Okay, so in the last lecture before the exam, we were talking about some kind of relationship between functors and natural transformations, and we reached pretty much after the lecture actually, so maybe I will revisit this later today, in the idea that like functors, if you think of them as wrapping some kind of values in some kind of computational or not so computational context. For example, we have a list of integers, we have maybe integers, we were talking about these examples, and what a functor associated with lists will do, we say, programmers will say the functor maybe, like this type class is a functor. Technically, what we know, I hope by now that is going on, is that we have list, the actual list is a functor because I can apply it on objects, which means types, and it gives me a new type. So if I have A is a type, then list of A is also a type. And I can also apply it on functions, on arrows. So if I have an arrow like that, I can get a function from list of A to list of B. We say that we lift F. It was like a little function from little a's to little b's, and now it's like a big function from list of A to list of B. And like in Haskell in general, in functional programming, you will see this like f map of F. But technically, it doesn't make sense to change this. This is the actually double character of functors that I can apply them on objects, and I can apply them on arrows as well. So this thing is the F map, this is the type of list of A, and this is the type of list of B. And the idea is that the laws of F map force you to not change this kind of structure that you have. The example I was talking about after the class ended last time was like, if you have a tree of integers, like let's say, or natural numbers that looks like that, and you apply let's say I have a tree, like, and apply a tree f to all this thing, I know that the shape of this thing will be like that. I don't know what will happen here. The idea is I will apply this function here, but if you look at the form of the tree, it's exactly the same. There's no way that if I apply a functor, I will end up like with a tree like that. So it doesn't change the structure of the package, if you want. It may change the values. And in this sense, the natural transformations are like orthogonal, because the idea is that you have something that gets you from, let's say, a list of alpha to, if I have a natural transformation from list to maybe, this is like a function that gets me from list of alpha to maybe of alpha. And now the idea is the exact opposite. I cannot really do anything with the values that I find packaged there, because it's a generic alpha thing I know nothing about. It's a polymorphic function. And since I know nothing about these things, for example, there is no way that I will get a new value, like adding two of the values I will find inside this list. I cannot add them because maybe this type has nothing to do with addition, right? So I can, and also, so the only thing pretty much I can do is maybe remove some of the values, because I can always do that. And I cannot forget these values and say, I will come up with a new value, right? Because how do you come up with a new value of a type alpha that you know nothing about? So in this sense, like the natural transformations are kind of orthogonal to functors, in the sense that they are not allowed to change and modify the values, but they kind of change the packaging. It's like they repackage the things, right? I just wanted to mention this. Probably I will not get further into this now. Maybe we will check if there's time in the end, like some silly example to see what the naturality condition means. But I wanted to mention this because I realized that it was not, we had a small discussion after the last lecture, and it was not like recorded, and a couple of you guys were not here, so okay, so here it is. Any questions? No, okay. So, I will start with the main thing of this lecture. because if I leave it for the second hour, probably will not have time, and I will push backwards the whole thing once more. So we know this connection between propositions and types, and we have probably written down this table a lot of times. We have been developing a lot of type theory, and we know all of these guys here. Am I forgetting something? So when I say we know these guys, okay, maybe the exam showed that we don't really know them so well, but anyway, let's say we do. Let's say we studied after that. I mean that we know the formation, introduction, elimination, vita, and eta about each of these type formers, let's say type constructors. And we have this connection with logic. Can somebody help me here? So just to convince me that I'm not talking by myself. Like the first thing corresponds to what in logic, yes? Okay, let's say conjunction, go on. Okay. Somebody help? Yes? Existential and for all, right? Okay, so one thing that's missing that we have mentioned it is like, the equality that we tend to use a lot when we are forming logical propositions. And it's like, have we seen something about it here? I don't remember this actually. And if I try to scroll, there's like 155 pages, so I will not do it. Okay. We kind of have. I think that we kind of have. It's the emphasis is in kind of. So let's call this for the time being ID. And let's quickly remember what's... okay, so there is a basic idea in logic that we have not discussed, and this is the idea of a predicate. So example of a predicate like is something like is even. So usually, like in the first or second lecture, if I ask you what kind of type of thing is this is even, you would probably say that it's something like from integers to, okay, maybe if it's the first lecture, you would probably say to booleans, and then you understood better the situation here, and you say, okay, it's some kind of proposition, so that if I apply is even to some integer, this will indeed become a proposition. I don't consider it as a truth value, it's not a true or false, it's the proposition that expresses the fact that 42 is an even number. Okay, so a good question is like, how do we express this kind of things? What's the correspondence of this kind of things, like predicates on some kind of type? Because I have a type here, maybe I can write it like this to look more like a type. I have a type here. How do I get this idea of a predicate on this type? And this corresponds to the idea of type families. Just as a reminder, like if I have this thing, then is even of A is a type, and now comes, it looks like I'm substituting type or prop, but this is the whole idea. The whole idea is that I'm going to use types for propositions. And the whole idea is that we will never see something like that here, because type theory has embedded in it its own logic, let's say, so it doesn't need this external help from something else prior to whatever foundation we're doing here. This is in contrast with set theory, that you have the axioms in set theory, but even to state them, you already need to have something like first order logic or some kind of other logic that you will state your axioms, and then together with the rules of the system that you're using, you will be able to infer new theorems. So here we don't have this prior thing of logic, we're just defining types in the usual sense, and we notice that as soon as I have these types, and notice that I can have many, many more other types here, I can have the programs or computations that do not correspond to something in logic, and in this sense, it's like this is the world of computation and types, and within it we find a subset that we can do mathematics in. Okay, so does this expression make sense, like the thing I wrote here, because I will need this a lot, and in general the form that it will have will be something like that. If I have A of type, little a of type big A, and I have some B, which is a type, then this B may depend on A, and I can emphasize this by writing B of A here. But I mean, even if I don't write it, sometimes we omit this. The idea is this: you are judging this, like you are asserting this thing, but you are within a context. You have some premises, some hypotheses, some objects lying around, and here are the things you have. So, like, as soon as you have an object of type A, an element of type A, this thing is a type. So this depends on the other thing. Yes. Exactly. As predicates as dependent types. Are you okay? Yes? Like is even will become a dependent type. Like you give me, because it depends on the integer that you will give me. And now that you gave me an integer, I am a type. What type? Which type am I? The type of all possible proofs that this integer that you gave me is even.
Can you repeat the last part?
Yeah. So when we see propositions as types, a useful thing to see it, because types, we think of them as like set-like things that have elements. So if I see a type as a proposition, which proposition can I mentally think that it is? If I say proposition as a type, which type is this proposition? Think of the collection of all possible proofs of this proposition, and this is the type of this that corresponds to this proposition. So for example, for is even 42, maybe there are 5 ways to prove that 42 is even. Okay, it's not a good example in this case, but we will see better examples. So if I say that something is of this type, it means this is a proof that this is valid. This is a construction of this proposition. Okay, and I can have more elements there. And since types come with their own equality, now we have a concrete way to take 2 proofs, because they are elements of the type of propositions of something, 2 proofs of the same proposition, of course, I mean, and ask if they are equal, right? Yes, is the question? No. Is that okay? Okay.
Εδώ πέρα, ως dependent type, το indexed set, ας πούμε, θα είναι το A και κάθε dependent type θα είναι μόνο για το εκάστοτε A, απλά θα είναι όλες οι αποδείξεις.
So BA here, I mean, I don't want to say now that it's a proof, because maybe this kind of type here is like something that doesn't have a propositional interpretation. Like it could be like a game of Tetris. I mean, it doesn't mean, what does it mean to prove Tetris? In this sense, like its computation is like more general. Or maybe it's kind of counterintuitive to think like this thing. I mean, you could do it, but it's kind of weird. What is this proposition? What does it mean? The natural numbers as a proposition. You could say that it means that the natural numbers are inhabited, and I have an infinite number of different proofs, one for each natural number. It's kind of ad hoc, I mean, this particular thing, but this example is not ad hoc at all, because we are used to see that things like is even, and we consider them like as predicates, so as soon as they get an argument, they become a proposition, and this proposition corresponds to all possible proofs that this proposition is valid. So, yes, this thing can depend on this one, but notice that maybe I could have more, and right now I will introduce the type of equality that needs 2 things, actually 3, and maybe you will spot what is the third one. Okay, let's start by writing it completely wrong first, and pretend it was intentional. Let's call it identifications between A and B. This idea, you can think of it like identifications is a good word. Things that 2 things can be equal. Ways that in which 2 things can be equal. And there are a lot of types that The type of identification is a subsingleton, which means that either they're equal or they don't, and there is no sense to ask in which ways they are equal. But just to give you an example of something that can be equal in more than one way, it will be like two groups, because maybe you can find, or two sets, because maybe you can find more than one isomorphism between them. So you say, okay, now I have two ways that I can identify this object with this one. We are used to identifying like groups as soon as they're isomorphic. I mean, when you're doing group theory and you say there are 5 groups with this property, you never consider like isomorphic copies of one group that you just rename the elements. You never consider them as new groups, right? So there can be more than one way that elements of a type happen to be equal with each other. Some types don't do that, and just to not get confused, if you see this word inside type theory, a lot of times props are defined to be types in which you have at most one way to equate elements. This is not the convention I have been following in this lecture, but anyway. So, like in this case, I would like to say that this thing is a type, and I like to think of this as the type whose elements are all possible ways of identifying A with B. Has somebody spotted a mistake here? There are 2 mistakes here. One is I think easy to grasp, and the other is kind of more tricky maybe. Yes? Instead of A and B, uppercase, what you said? Να έχει, δεν βγαίνω τι λες, να έχει κάποιος Μανώλη βοήθα με, είσαι πιο κοντά. Like that? Κάπου λες ότι πρέπει να βάλω ένα A κεφαλαίο και ένα... να είναι κάπως έτσι, A, B. No. Χωρίς αυτά. Αυτό εδώ λες. Αυτό θα πω... Okay, this thing, I could also write it like that. Right? In this way, I'm writing the same thing. It's just that I'm not emphasizing the dependence of B on A. But even if I don't emphasize it, it's there because this judgment happens only within this context. And whether it actually used it or not, it's its own problem. So as soon as inside of this thing appear some A's, I mean, they refer to this thing. And if they don't, it's a vacuously dependent type. Like a family that doesn't really change. It's always the same thing. Lazarus?
Small a and small b on the left should not have an arbitrary type, but be of type.
You started very nicely. You mean these things should be type? That's what you mean?
Yes.
Because
I think the idea behind the identification is to compare 2 types.
We want to compare to compare elements of whichever type. So, for example, this could be like the integer, because I want to have a way to say that 3 is equal to 5. Whether it is equal or not, I want to be able to express this proposition, right? So 3 is not a type. So if I limit myself on this thing, it's kind of too limiting. But you are right that there is a problem there, because you changed A and B into type and type. Manolis wants to say something, I think, on this.
It should be the same type.
It should be A and A. And A could possibly be this type that you're thinking about, the type of types, let's say. So the major mistake here is that if it was like that, I would have like a type that corresponds to identities between an integer, let's say, and a person. And it's not that I want to have this type and not have elements because it's like false. I want it to be not even possible to state that Manolis is equal to the number 42. That's, I don't want this to be false. I want this to be nonsensical, right?
Why is that better?
Why is that what?
Why is that better?
Because you have like a system, a foundation that doesn't allow you to ask like nonsensical questions, so you immediately know that this thing that you're trying to express has no meaning. It's not, I mean, imagine if you're trying to prove something while you could already have a hint that what you're asking makes no sense. So you are forced to work in a more tidy way. You will not, I mean, in the first examples that I gave in the first class, first lecture, I think you will remember I was asking questions like if the cosinus function belongs to the square root of 2. And it's, I think, like obvious that even if you are a hardcore like set theorist, you would say this is nonsensical. This question is nonsensical. Now, but if you take your foundation seriously, you will say that I cannot even answer it because does it or does it not belong there? It really depends on how you ended up constructing, let's say, the square root of 2 inside your system and how you ended up constructing this. But if you're working in set theory, this is a normal question because after all, this is just a set and this is just a set and everything is a set, so all possible questions make sense. So this is a completely different mindset that we want to have help. And the help is not only to protect you from what you are asking here doesn't make sense. It's like from the context, the typing context that you give, you get instant help from your system. Like the only possible thing that goes here from the context is something of this type. So if in your mind you were thinking that you're constructing a function of this thing, and here actually by the context I'm expecting an integer, somehow you know that you have miscalculated something. It's like a very good help to have and have things organized like in your mind. So first problem is fixed. We only want to permit but sorry, just to make this point stronger, it's not that I'm saying that the answer here will be like if you ask me to find a proof of this thing 3 and I don't know Manolis. It's not that I'm saying, I don't know because this is a very weird type that does not exist and I cannot answer this. It's like I'm in a much better position from someone who would be trying to prove this or trying to refute it, even managing to refute it. I know that it's worse than false. This thing that it's not even expressible, it's not in the sense that it's unknown, it's a gray area or something like that. It's like, it's even worse than false. It's a nonsensical thing. It doesn't make sense as a thing. Okay, so what's the other thing that's missing? Probably he will not spot this because I have been making, there's a convention that we don't write these things down and they are kind of always implicit when we write these things. I mean, where did big A come from? What was it this? No.
Should it be ID with the subscript of big A?
We are getting better and better, yes. Okay, so one thing that was implicit there is that this thing depends on this A thing, right? And yes?
And a type.
Yes, and big A, what is this big A, right? So big A is a type. And notice that every time I'm writing a context, we haven't done this a lot here. So this is, I think that in the lecture I was planning to do this, I ended up not getting there and forgot about it. So I think I have already mentioned that this is written as a context of this judgment. This is a judgment, this is the context of the judgment, and this is the assertion I'm making it. And it's a hypothetical assertion because it depends on this context. A lot of times we write like gamma as a generic letter for a context. And the question is like, what kind of things are contexts? So I have this like typings here, and the idea is that the first type that I will write must be something that, so if I write something like that, I must know that this is a type, somehow. This should not depend on anything. But on the second thing that I will write, I'm allowed for this thing to depend on the previous thing. And the third thing I will write, its type is allowed to depend on the two previous things. Does that make sense? And when I say two previous things, I don't mean the two previous types, I mean like the two previous variables that I have inside these types. Like I have a little a of type A, and I have now a little b of type, and this type depends on this a. And I have a little c whose type depends on these two values, right? These are the dependent types I'm talking about. So, and this goes on, right? And then at the end, on the other hand of the turnstile, I have like something that can depend on all of those things that I have on my context. Yes?
If we want it to be like kind of pedantic maybe, should we also write B of A and C of A and B are types?
So when you write this, a very good question, the idea is that you already have somewhere that this thing is a type in the previous context. And this thing is a type in the previous context. Okay, so yes, and in order to write this thing down, you should have some kind of way of guaranteeing that as soon as you have this thing, this guy is a type. And as you have this thing, this guy is a type. And this goes on for the whole of list of contexts. Any other questions? Okay, so now that we have like an idea of how we can express this and what it means, like to say that I will see is even 42 as a kind of type whose elements are all possible proofs that is even is that 42 is even. Let's try to see how we could write something. Okay, maybe is even. Let's try to define is even. Like what would this type be? Okay, so it takes like some integer, and then which type will it become? I mean, like is even. No, I'm not saying it properly. Okay, let's say I have n, which is an integer. Is even n, which type should be the is even of n? That's my question. Yes? Okay, no, wait. We don't want just the truth value of this thing. We want a type that expresses the proposition that n is an even number. Let's try thinking of it as a proposition like this, and then translate it to this, because I'm trying to write a type and not a logical formula. I'm trying to write like a type. Yes, Lazaros?
Type. I don't think.
Let's start with the logic thing. Give me a definition like with a logic formula. Okay, what does it mean to be an even?
2 divides.
Okay, that would okay. It's like 2. I could say like divides. If I want to make a 2n, or I could even write that. But now I will ask you, what does it mean that something divides something? So we need to remember what it means that divides. How I'll define this? Divides A, B should be what?
B can be as A times n.
So how do you write this as a formula? You're right. I mean, let's translate it into symbols, into a formula, so that we can translate it then into a type. So let's first translate it on this, so that we can eventually translate it on that. Manolis?
The formula would be there exists k as an integer such that b is k times a.
Such that a k equals b.
Type-theoretic
So we have everything. We can translate that, right? Okay, so let's translate this into a type. This would be?
It should be the sum over k integer of the identification of, well, if we have the n above, we would do n and 2k. Here we have a, k, and b.
Okay, I don't know if this parenthesis helps or not. Okay, maybe. Okay, something I didn't mention. We do actually use this notation. Instead of writing this, we do actually also have the notation that looks much more like a proposition. We do write it like that. Okay, so if I write it like that, it looks more and more like that. Pretty much just the existential becomes a sum. And okay, I could write it like that then. Let's see. And obviously, since I can infer this type, I don't need to write it. But since I'm doing things like in detail now, I will write this int here. Okay, so are we okay so far? Yes?
Μπορείς να ξαναδείς ποια είναι η διαφορά του να πούμε το boolean και αυτό? Δηλαδή θα βάζαμε ένα τελεία και θα λέγαμε κάτι μετά.
Okay, so the type bool, okay, it's a very common misconception or confusion thing. The type bool has two elements, right? False and true. So this type and expresses like a truth value. It doesn't express a proposition. Like if I say, let's say, this course takes place in Greece, its truth value happens to be true, but like I have tons of different other things whose truth value are also true, but they say different things. So the type of proposition is much richer than the type of booleans, because it's like things before you translate them and you ask if they are true or false, and you map them to a truth value, you want access to the original thing that has an infinite number of propositions. And if you look at this specific one, this is a type of all possible ways that you can prove that A divides B. In this case, probably there's only one, okay, so it's not so clear, okay? But the idea is that I want what is expressed by this proposition. I don't want the final result. It's like, just to emphasize a bit more, if someone asks you, like, what is the difference between sums, expressions of sums, and integers? It's like, wait a minute, 3 plus 5, I can see, it's a sum. I understand it as the addition of 3 and 5, and while this thing is its value. So maybe I want to study expressions of addition, and which have an infinite number of them, and not just like the end result, right? Okay, so now I'm just writing in a different way, like the same thing translating into types. I already have a type here. I've written it in a different way that maybe looks more intuitive. And let's remember a different notation for sigmas. So let's remember this thing. What are elements? Okay. What are elements of a sigma type look like? Does someone remember? Yes?
Για το κάθε k ένα στοιχείο από τον αντίστοιχο τύπο. Από τον αντίστοιχο τύπο.
This is a pi type. So if I understand what you're saying, if I have something like that, it means...
Όχι ένωση από κάτω για όλους τους τύπους, ένα στοιχείο, ότι...
You mean you're picking for each integer a specific, for each type a specific thing?
Ναι.
So this would be the pi type. It's like you have, this picture is good to have to remember it. Like, think of this thing as the indexes,
No.
right? So this is the second type. these balloons here are like types hovering over the base type over the index, and
Το σήμα θα είναι ένα σημείο.
exactly. Okay, this way. So you were trying to describe. Okay, sorry, maybe I understood it incorrectly. So you have a bunch of things here. So as soon as you select, so an element of the sigma type would be like, this is my point. It's a pair of two things. And I can project, and I can get the first projection and the second projection. So the first thing of this thing is the shadow, let's say, this type, the index. And the second thing is this thing. Okay? While for a p-type, the image is kind of similar. But remember that for a p-type, elements of the p-type are functions. And the idea is that you need to pick one for each of these. And remember, these balloons can have duplicates. Maybe it's even the same type, right? It was, this is actually how I can implement the function type as a p-type to understand that p-type is just a generalization. So here, your elements look like that. Okay, like there are sections of these fibers of these balloons that hover over there, while in this thing, this is one, the blue thing is one element, and the orange thing is a different element of the sigma type, while here is a blue element and here is a different element. Okay, does that make sense? Okay, so coming back to my question, this is actually a pair, which means that its type, I can also write it like that. I have mentioned this alternative notation for sigma types, and I think it's way more convenient sometimes. It's this times, so the first coordinate is an integer, but I need to give it a name. I will not say integer times something, because this something needs to know which integer was there in order to become a type. This is the idea of a dependent pair, because the type of the second component of the pair depends on the first component. Okay? While if I write something like that, I mean, in the usual Cartesian product that you see, like in set theory or something like that, you don't have a direct way to express this. I mean, what are these elements? What are the types of the elements of this type? It's pairs of an A that belongs to a big A, and a little b that belongs to the little b. You already know what the type of the second thing is before knowing what the value of the first thing is. While here, you want to say that this depends on the little a. The second type depends on the little a, so you need to say something like that. Okay. So in this notation, this pair is an integer. Let's call it k, and the second component is of type a k equals b. Okay, so if you have something like that, let's call it a w of this type, you can do all the things you can do to pairs. You can take the left projection, and its type will be an integer. And you can take its right projection, and its type would be, and this is a good exercise to see if we're understanding what's going on. What would its type be? I can take its right projection because after all it's a pair. And the question is, what is its type? Yes, Konstantinos?
It's a prop.
Well, what?
It's a prop.
Narrow, you say this? What was your answer? We're still not there. Okay. Okay, but I want. It's easier for me to say why it's not a prop. Well, actually, I will consult more answers until we'll get it. Maybe Lazarus. Type. And Manolis.
A times WL equals
Okay, yeah, that's the one. Okay, but let's see why. Why these things, the first three suggestions don't work here. The type of whatever you gave me here, let's give a concrete example. Let's say that let's say that A and B are, I don't know, 3 and 12. Okay, so the type of 3 divides 12, all of its elements are pairs. The first component is like this K that I have here, so it could be 4, and the second component should be a proof that 3 times 4 is equal to 12. If I allow the second component to be any kind of type, you would think that it would be convincing to give you something like 7 and here a proof of the Pythagorean theorem, let's say, and you would consider this as a valid element of the proposition that 3 divides 12, and this doesn't make sense. So the type of the right-hand side, it's pretty much the proof that the witness that you chose is in fact a witness. So if I leave it as too general, like say proposition or type, you will permit the second component to prove something completely arbitrary. While when you want to prove an existential thing, your proof is like a pair of things. First of all, choose your witness, and then we don't say, and then prove anything you like. You have to prove that your witness is in fact satisfies the thing that we were trying to satisfy, right? Does that make sense? Okay, there's a question. Arati. Actually, no, Manolis nailed it here. I mean, let's write down what Manol said, because with this example, maybe it helps us reach what Manolis said there. Okay, say it again, Manolis. So, like... So I want to say that A times the witness is indeed equal to B. How do I get the witness? Okay, it's a very bad, sorry for that. It's a very bad name, because W is the first letter of the witness. This was coincidental. W is not the witness. Okay, let's call it, I don't know, P, to think that it's a pair. So here it's like, or a proof. So the left part of this pair, which is also called witness, in this case, is an integer. The right part of this pair should be a justification that the witness is indeed a witness of that. So it should be something that A times your witness is indeed equal to B. And what is your witness? It's the left projection of P. Okay? And this is always the case. I mean, when you're forming things like that, the type of the projection would be this one. I mean, not this equality, but it would be what you get if you substitute this your case with the left projection. Any questions before we get to a break? Okay, small break. No questions about this during the break, okay? Because I want to record it. So let's have like a 10-minute break. Okay, so in the break, Manoli spotted a mistake here. So I was saying that this is an example value of divides. I was saying something like that. That this is an example value of this type. Not AB, sorry, 412. But it is not because like this thing is indeed has the correct type. It's a 3 and 12. I'm trying to convince you that this is very trivial and easy, and I'm making tons of mistakes. But this is my problem. Like I'm the problematic thing here. So now it's correct. So indeed 4 is a witness for the fact that 3 divides 12, but the second component of this pair should not be a type. I mean, should be an element, a proof of this equation. So there may be some kind of identification of this type. Okay, it's not the actual type. Okay, so Similarly, maybe if I want to see something like, if I want to express the idea, the transitivity of divides, like how would I express this? What would it mean that this relation is transitive? And again, okay, I'll let you think a bit about that. Like, what would be the first? Let's go to logic, and then let's translate it to types. Yes. Exists for the transitivity.
Να υπάρχει κι άλλο νούμερο στο τέλος που να...
What would you say? Exists what? Say.
Υπάρχει ένας αριθμός, ώστε αν ισχύει ότι υπάρχει ένας αριθμός και ότι υπάρχει και ένας άλλος αριθμός.
Wait. No, wait, because the transit. Okay.
Αν υπάρχει ένας αριθμός που να έχει την ισότητα και ένας άλλος αριθμός που να έχει την άλλη ισότητα, τότε υπάρχει κι άλλος ένας αριθμός.
It's kind of weird because the way you pronounce it. Okay, first of all, it looks like an implication because you said an, blah blah blah. This is more or less correct, but it's not actually an implication. I think you are looking too much inside the thing you want to express. Eventually, there will be some existentials there, because hidden in any kind of expression like that, it's an existential, right? This means that there exists a case such that blah blah.
Divides, cannot divide.
Do we have some yes?
For all ABC integers.
Yes, it's like for all A and for all B and for all C, something happens. Okay, so in this case, okay, let's write it like that first. For all, I will write it like in abbreviating form. What happens?
A divides B and B divides C implies A divides C.
Exactly. B and B divides C implies A divides C. And now let's translate it into its type-theoretic equivalent. So here there are three for alls, right? So this will be, yep, P, let's call it A, P, B, P, C. Notice that it could happen, it didn't happen here in this example, but it could have happened that this type could refer to this A. It didn't, okay? And this type could refer to B, and it could also refer to A. It didn't, okay? But what I will write here will end up referring to all those three things. The type I will write that will end up depending on those things. Okay, and here I need a way to express this. Somebody else can help me? So I need to translate what kind of formula is this? What's the race of this formula? Is it the weird divides? Is it a conjunction? Is it an implication? We need to remember where the implicit rules of where I put parentheses are to reply to this, or just understand what this says. Yes? Okay, so this whole thing that I'm trying to translate is an implication. Something implies something. It's not a conjunction. It's not this and that. It's that this implies this. So I need to remember how I translate implications. Why do I do that? In type theory, implicate, yes? It's a function. It's a function, right? Okay. So the right-hand side should be a type that expresses this idea, and I have exactly this type because I defined it here. It's it's this. I could add a syntactic sugar. Nobody wants to write divides A, B. Okay, I want to write the notation I want. So this is sugar for that. And which type is this type? It's this type. Sorry, it's this type. Okay, so I can write this. I have already defined A divides B as a type. Okay, so what do I have on the left? Yes. Exactly. So it's the A divides B times B divides C. And maybe I don't need to do that, but I mean it's the first time I'm writing this thing, so it's maybe yeah, it's good to put these parameters there. Okay, so let's translate this again in a different kind of notation. Remember that pi's are just functions, so in the same sense that I translated this into that, it became obvious that its elements are just pairs. I want this to become obvious that its elements are just functions, so I could write it like that. It takes an A of type int and gives back this, which is something that takes a B of type T, of type int, and gives back something that takes a C of type int and gives back something of this type that I don't need to name it because I don't need it on the consequent types. So it's like A divides B times B divides C. And finally, this becomes this. Okay? So if I want to, let's say that to enter this like mindset of seeing types as a proposition and elements of types as proofs, let's say I want to construct an element of this type. My objective as a mathematician that proves things becomes the same objective as like a programmer who wants to program a function of this type. Like an exercise, write a function of this type. Okay, so how would you write a function of this type? Let's call it f. It's not a good name, but anyway. Okay, I need to name my arguments, right? And here I already have like those names. It's like A, B, C. Okay, I need to name this argument. How would I name it? G. Okay, it's a weird name because I have F. No, it's not okay. I don't like G. A different name. W. Later on, I will complain about this W, but let's call it W because it's like a pair. And now, finally, I need to produce something of this type. Okay. So, what is the type of those things? A. So here, so when I try to define my function, in my context, I have all those things that I received as arguments, my function received as arguments. So you got an integer called A, you got another integer, and you got a W. What's the type of W? Yes? No? That's the type of W, okay? So you have something of this thing. And you say, aha, what do I want to produce here? What's my goal? I need to produce something of this type. Okay? So essentially, I need to produce a pair. The first element of this pair, so I can even start writing like that. I need to produce a pair. The first element of the pair must be some integer, and I need to think which of these integers will be. And the second element of the pair must be a proof that my integer multiplied by A is equal to C. Does that make sense? Okay. Before I go on, and maybe I will pause and keep talking about something similar, related, sorry. I could also use like, okay, let's try to do this proof as if we are in the first semester number theory or whatever course. What is the witness here? How will I obtain the witness? I cannot put 42 and expect to work, right? Yes? If you say A, you are claiming that A times A is equal to C. And there is no reason to believe that. We want to find what we can put inside this box here, right? Probably A times something is equal to C. So I need to use these things that I have here, right? To obtain a witness for this, obtain a witness for that, and probably use these two witnesses somehow in order to put something here that fits, right? You have a different idea?
No, Καλά, μπορεί βασικά δεν θα είναι το A
You're saying the value or the result of A divides B, that's not, say the correct word? Exactly. Okay, so here, you want to ask, what is the witness of this? I do have this thing, right? It's here. Wait, the left of what? The left of A divides B.
No.
Okay, which is the left of W, right? Okay.
Then go left.
Yeah, exactly. So if you go to the W, which is a pair of proofs, one that A divides B and one that B divides C, you extract the left part, which is a proof of A divides B. What is the type of this thing? It's a pair of an integer and a proof and an identification. So we want to get the integer of this part, okay? So we need to extract this thing. And now what's the type of this thing? It's an int, very, very nice, okay. And I also need a different int, and I need to think what I will do with these two integers, right? So where will I obtain the other integer? It will be like, go to the same pair, which is like this. Now get this value, which is like, give me the right-hand side thing. And now, left or right, yes? Left again, yes, because I need the integer of that. And what I will do, what will be, so we already have the correct candidate for this place. It looks weird, it looks very tricky maybe. And it looks so weird because we didn't have help from the paper. Because I'm digital paper, right? I'm writing on a paper. Probably in a couple of years you will be writing in a tablet and you will see the type errors. We're not there yet. But I mean, I could write any kind of, I could write 40 times 42 here and my tablet doesn't complain. But if you write it in Nagda or something like that, that type checks those things, and you try to write something, anytime I'm trying to write something, I don't have any immediate access to all the things I have, these things, and to what is the type of this particular thing, of this hole that I'm trying to fill, right? Okay, so here it will not be 42. It would type check. I mean, this thing times 42 is an integer, but in this case I will never be able to find an inhabitant of a reason of why this integer works, because it doesn't work. So here I would have to say WR left. And what do I need to put here? I need to put here an identification of my integer times A and C. So here would be something, what is the type of this thing? It's a type of A times all this thing that I wrote there. With C. I need to come up with an identification like that. Make sense? No, if I put this inside, I mean, I'm sorry, you're confused because I made this mistake earlier. If I put this inside, it's exactly this mistake that I made here. So the second component of this pair is not a type. Its type is not type. Its type is a very specific type. It's this type. So the element is a proof of this equation. It's not this equation. We call this proofs of equations. A lot of time we call them identifications or even paths, because there is a way to interpret types as spaces, and we say that, like, if I have a space like that and I have A and B, to identify each identification between A and B, I can see this as a path that gets me from A to B. And then I can have like more than one paths, and maybe I can compose two paths. This would correspond. Okay, we'll come back to this in a few minutes, I hope. Okay, so are we okay with the types that I have written so far? Okay, some like annoying thing is probably this. I could do this if I have programmed in any like functional programming language in my life. I could never do that. Can one of the programmers here say what's ugly in the way I'm treating these arguments, particularly one argument of these? You would never do that if you were writing like Haskell or Agda or something like that. Yes?
Totally.
Yeah, I mean, what's the point of giving a name to a packed pair if eventually I will have to look in its left and in its right to obtain its values. I can use pattern matching. I think we have seen this. But I mean, you see it ever since elementary school in mathematics. When you define a function, you say something like that, right? Blah blah blah. You are doing pattern matching on the pair. You don't say f of w, which is a pair, and then anytime you want the first component, you do w.1, and then w. I mean, you can do it, but it's not so convenient. So here, if I write this in a kind of better way, I could give more indicative names, sorry for that. On this, I could say like f of a, b, c, and now w, I will do a pattern matching and I will give names to these things. I will call this hub, and I will call this hack. What I'm thinking about is, it's one letter, it's not a multiplication, H, A, B, okay? I'm thinking like it's the hypothesis I know about A and B, and the hypothesis I know about A and C. When you have your own conventions, you follow them, and this ends up helping. So it means that when I want to write what's going on here, I want the left of the hub, right, times the left of the, hack, trying to advocate that names help and I make mistakes. And then similarly the other thing. And so you have less bureaucracy thanks to this pattern matching that you're doing. I made a mistake, right? Yeah. So what, yes? No?
No, it's not a mistake.
Okay.
Would it be more reasonable, or at least as reasonable, to unpack both of these pairs as well, and then a pair of pairs?
Yeah, this is the second level of deepening. So since hub is a pair itself, I can do some nested pattern matching. And have here like the witness of A divides B and the, I don't know, the identification related to that, and similar like this. And now I instantly have in my context all those data that I want to do. It's like, instead of saying, give me this conjunction, extract left and name it like that, extract right and name it like that, you can say, okay, instantly look inside this conjunction and I will name like this the components of the pair that will match with this conjunction. Okay, so far so good. There is a big point. Okay, just 1 second. Okay, now actually, because I don't want to forget this, I want a way, just remind me after your question, you will be the responsible for that, to get rid of this ugly thing, and I will explain why it's ugly. I just said it's beautiful, because it's better than this, but we should never be satisfied with the beauty of what we are writing. We want more beautiful things. Yes, tell me. You are absolutely right. I knew I made a mistake. Anything else? Probably there is a mistake that I will catch later on and be annoyed. What, sorry?
Same thing about.
Yes, okay, thanks. Yeah.
Υποτίθεται μας δίνεται, ας πούμε, στη συνάρτηση και το W και οι δύο σχέσεις ότι κάνουν divide και με αυτά τα δεδομένα κρίνουμε το A divides C. Δεν είναι ότι το W υπολογίζεται μέσα στη συνάρτηση κάτω. Σωστά.
This W here?
No.
This W is an argument. I mean, you have access to it, and what you can do with it is completely determined by its type. So if you look at its type, it's a pair, so the only thing you can do to this W is extract its left, project left, and project right. Now, what you get when you project left has its own type, and what you can do with it is completely determined by this type. So its type, the left thing is A divides B, so it's a pair again, so the only thing you can do is project left and right. If you project left, it's an integer. What can you do with an integer? You can multiply it. So this brings us to your previous question that you asked in the break, like where did this multiplication come from? I forgot to mention it. It's defined in this type that I have, right? So I can refer to it because I already have that. I know that K is an integer, A and B are integers, I never wrote this, but I think I said it orally. All this thing happened in this context, okay? B is an int. And only if I have this, I have that divides A, B is a type, okay? It's a dependent type on A, okay. But I'm not sure if this was what you meant with like, if this answered your question. But
Όχι ακριβώς, αλλά δεν είναι πολύ λαθμένα ερώτηση.
okay, that's helpful too.
I think the question didn't make sense. I think I got what he asked.
Okay, help him, help me, help us all.
The reason that we have W as an argument is that we want to prove the implication. We want to prove that if we know A divides A divides C, then A divides C. We don't just want to prove that A divides C out of nowhere. That's why we have.
Okay. You could put it like that. I mean, you have the freedom as a prover or as a programmer to, if you want to pass this on the other side, it will become a lambda W. Okay, but I mean, if you say that I don't want to look at it, which sometimes we want to ignore some kind of arguments, like this is what you would write like in Haskell or Agda, you will have a problem because you will need to look at it, because you will need to use it in this case. If you wanted to prove something like that, which is valid, indeed you don't have a reason to look at W, you can just give 1 as a witness because A times 1 is equal to A. But if you want to actually prove the interesting thing, which is this, you will need to take advantage of all these facts that you have, and you will need both of these, so you will need this W. Okay, back to dissing and trashing this kind of thing. What's wrong with it? And this has something to do with a previous lecture that I was mentioning, that even though we have proven in category theory that all products, there is only one product, if there is a product actually, uniqueness of products and uniqueness of coproducts. What was that? If you give me A and B, and you give me some candidate that happens, in order to give me a candidate, you need to give me like a triple, right? Let's call it like that. And it needs to be the best among them, because if someone else give me another thing of the same type, which means an object and two arrows, one in A, one in B, and has to tell me which arrows this is, mine is the best one, which in this case meant it's a terminal thing, which means that there is a unique arrow that makes this commute and factors through P and all that stuff. And we have proven uniqueness, and even more, if you remember, we have proven an even stronger uniqueness than the usual unique up to isomorphism. Do you remember what it was? This is a very, very strong uniqueness thing. They are unique not just up to isomorphism, but up to unique isomorphisms. Because when you say just they are unique up to isomorphism, it means that any two things that have these properties are isomorphic. But they could be isomorphic in more than one ways. Maybe you can find more than one isomorphism. They are still isomorphic, and you say they are unique up to isomorphism. But in this sense, all these all these things defined by universal properties in a categorical way, they end up being not only unique up to isomorphism, but there is actually only one isomorphism between any other candidate and your thing. Okay, so they're very, very unique in this sense. And still, I want to make the case here that unique as they may be, I may care about the names. You may say, okay, but like L and R, out left and out right, you want the P1, P2, all these things are different. For what? For my human eyes and my human brain. So yeah, they're isomorphic, but like when I will go there to define divides, maybe I want to give a name to my projections and not be left and right. And a much more sensible name would be something like witness and I don't know, justification or equation or whatever. So now that as soon as I have something like this thing, the hypothesis I know about AB, this is a divide, it helps me much more to say extract the witness of this thing and extract the, I don't know, the equation or the reasoning of this thing, and so on and so forth. Does that make sense? Okay, so when you define these things, it makes sense to say, okay, I'll take a moment to help my readers and myself when I'm reasoning about this to pick good names. And now let's go back to the last thing I want to see still in this idea of P's and sigmas and how we use them in, actually it's the penultimate thing I want to say. Let's see if we'll make it. How would we define something like a group? Okay, ever since the first lecture, I've been saying things about a good definition and a proper definition of a group, and one that makes it obvious that it's algebraic and whatever. But even if you don't buy this thing and you say, I want to translate what I saw in the second semester, like in the math department, you can still do it. But like, how would you do all those things? And let's remember a group, I'm using this calligraphic fancy G, is a tuple. And now how many things you have inside this tuple, we might get into some silly argument, but let's pick my favorite thing and then see why it can become better and how it gets much longer and more useful in type theory. So, first of all, this symbol that I'm using, think of it just as a comma. It's like helpful for me to separate the carrier set from the structure. Okay, so it's something like this. I have an operation, I have a unit, and I have an inverse. We have seen this definition of groups together, so I know you know this. And probably, if you have seen groups before, you had seen something like just like that. But the definition never stops there. I mean, what's the let's see if I can find types for these things. Okay, ideas. How can I express this thing? What is the type of this thing? Yes? It's a tuple. Now tell me the type of each of the components. So, let's do type. Right? Okay? Okay, let's say that G is some type, okay? And what it means that I have a group structure on this type, let's say. There are tons of ways to do it. There's not exactly one correct way to do this, but I want to see at least one or maybe two ways to do this and appreciate the power of sigmas and p's and all those things that we have. So, and equations, blah, blah. So, it's a type times type because the type of the first component is type. So it's a Cartesian product of type times, what's the type of this? Lazarus?
I would like to give
Perfect. Do we all feel this? I mean, I could not say, maybe I want to write something like G times, you probably want to write something like that, right? But where did this G come from? You need to give a name to the actual component, the thing that's in the first component, right? The first projection there, and now you have access to G on all subsequent things, if you like. Go on. What's the type of the second thing? G, okay. Yeah, okay, G. Okay, G. I could also say 1 to G, which is isomorphic, if I want to think that the unit is like something that picks an element of G. They're isomorphic, it doesn't affect what I'm trying to teach at this moment, so let's take G. And the type of inv would be, yes?
No, I would ask a question about
Okay.
a unit. Shouldn't we also provide a proof that the unit respects the property?
Yeah, we'll get there, yeah. And you should have a similar objection one step earlier, because we need to say something about the op as well.
Doesn't the type we wrote satisfy? No, have the association.
Exactly. Okay. So let's first be done with the types of the data of a group, and then Because usually, the way we have been seeing it so far, it's like intermediate. Maybe I convinced you that I have more data, because I have operation, I have like a carrier set, an operation, and a unit, and another operation, the 3 operations, a binary, a zeroary, and a unary. And then we said such that some axioms hold, right? So it's like the data here and the axioms there. For us, there is no distinction between proposition and axioms that we know and data. After all these propositions have inhabitants, and these inhabitants are proofs. This is how we use our axioms and the laws that we have and the theorems that we have. So we will need to get these axioms and put them inside this big tuple. So actually a group will end up being 9 tuple, 7, we'll find out right now. Okay, so but let's go on with this thing. So what's the next type? Yes? G to G. Okay, and if I stop here, I haven't expressed the fact that this carrier set and these operations need to satisfy certain laws. So now comes the thing that 4 things are not enough. If you ask me for a G for 4 things, they are not enough. But just to get you in the mindset of giving good names, please agree with me that nobody should see something like this, 0.2, 0.3, and 0.4. Like, you have to remember that G.3 refers to the identity of your group. Please don't, okay? So let's give some sensible names. Let's call this carrier. Let's call this op. Let's call this unit. And let's call this inv. Okay, so if you give me something that is of type group, now I know that G.op refers to this projection that has this type. Okay, so we are already in line, like in good things. The only problem is that it's not a group yet, right? So let's make it a group. So this thing is wrong. Okay, luckily I will not erase it. I just need to add more things to it. Yes, Konstantinos.
Για το G-type, πριν που είχαμε σχέδιο type, τώρα δεν έχει καμία διαφορά. Ας πούμε, γενικά ο τύπος type κάνει collapse άμα είναι εμφολευμένο. Γιατί άμα είχαμε το G...
This G, right? Or the calligraphic one? This G,
αν ήταν dependent, ίσως. Βασικά, τέλος πάντων, ρωτάμε αν κάνει ενδιαφέρον το ότι στην αρχή είχαμε τύπο.
Wait, when we started as a type, I mean, I think Lazarus was who said it, said, wait a minute, I need to know the name of this thing. Because how will you express that this thing needs to be a binary operation defined on this type?
No.
Right? So if I say type, I have no way here to express that it's a binary operation defined on the element of this thing, which I need to give it a name, and as soon as I have a name, I can say, the second component, what is its type? It's a binary operation on G. Where did I find this G? I need it here.
Ναι, απλά δεν είναι πολύ καθαρό ότι στη μία περίπτωση έχουμε τον τύπο τύπος και στην άλλη έχουμε έναν τύπο τον G. Δεν ξέρω αν αυτά τα φέρνουμε διαφορετικά.
Wait, this is a type. Okay. This is a type, and this is also a type. The second one happens to be dependent. The first one happens not to be dependent. But for this purpose, it's not an essential thing, I think. Maybe it will become clearer as soon as we fix what we need to fix here. So any suggestions? Like, I'm on a good start. I have started in a nice way. First of all, I have 4 data, and I have given good names to it. Please do that. And okay, what do I need more? Yes.
Okay, to start with, we will have something like times A, B, C, D, which have type
So you're trying to express which idea?
that the operation is associated.
Perfect. Okay. So instead of like translating everything like that, we could do something like, I want to say that which operation is associative?
Oh,
I named the projections. Okay. So I could do something like that here. I agree. But like, what else could I do?
we could just name also.
Yeah, let's name this thing. And let's name this thing, I don't know, maybe you want unit, maybe you want E, I don't know what you prefer, but okay, let's do unit. And let's name this like okay? These things do not have to be the same name as this. Probably it's convenient, maybe you pick something else. But it's like the projections. Right here, I need names because I reached a point that the proposition, the type that I'm trying to describe here, needs to refer to more things than just the things that had a name so far. It needs to refer to this operation. And instead of trying to express that this operation is associative in a low-level language, what does it? It will be P, 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 right? A, B, C, and blah, blah. Okay, op times, and let's stop here. Let's think what this thing means, because I don't get to write assoc open and hope that my system will understand what it means. So how would I define, what would the assoc thing, what's the type of this thing? So you should be able to express, a lot of times I will want to say that an operation is associative. So that's why it's a good idea to give it a name. Yes, Konstantinos? So what is the type of the actual assoc thing?
Type. Ως όρισμα και validity pro.
Let's start with a small mistake. I think you're trying to reach the final answer here. Let's say that it gets an operation. So let's give it an argument. This should mean somehow that this should be which type? The type that says that for all A, and I'm not sure what I will put here, and for all B, and for all C. What is that? Op of op A, B, C is equal to op, maybe help me here because I might make a mistake, but I think it's this one, B, C. Let's try to fix what needs fixing. First of all, is this correct? To operate A and B, and then operate this with C is the same as operating A with the yes, this is correct. This is associativity of op, okay? What do I have here? And it's like, you can think of this as like parameterized. So this thing also needs some kind of type here. And these all will be of, let's say, A, big A. And all those things will be like that. Does that make sense? And what is the, so if I want to say now what the type of assoc is, should get, let's see, an A, that is a type, and an op, whose type is what? Yes? Yes, binop, I liked it. A binop on A, and if I ask you to remind me what this is sugar for, it's just A cross A to A, okay? And what else? And all those things. I mean, you could copy, now you can copy this here. Okay. And obviously, when I'm defining what a group is, I would really like to see this as like that and not like that. Okay. And similarly, I will leave this as an exercise for you to do it. I need to define how do you think I should express this? Let's say, okay, I will give it a different name. It will be helpful in what I want to say. Now I need to express the fact that what? Yes? E is a unit for the operation, right? So here, this predicate is a binary one. It's like that unit, and what kind of unit? Left or right? It's a both-sided unit, so it's a unit. Which is a unit? Unit E for op. And so as you understand, this will be just a pair of things. Will mean that it's a left unit and that it's a right unit, because I will define unit to mean this, because essentially I will want to have access to the idea of left units and right units. And the other thing here will be I want to say that this guy here, what this guy returns is indeed an inverse of its argument for this operation. Okay, so here I will have something like it's indeed an inverse what? Yes?
Το G και το O.
What is G? Wait.
Ο τύπος. Δεν χρειάζεται και στα υπόλοιπα επίσης.
Probably, yes. Okay, I'm used to some comforts that we actually have of implicit arguments. I mean, sometimes when something can be inferred from the other arguments, you declare it as an implicit argument, and it ends up being given like for free. But you're right. I mean, here we just said that. So you would write this probably in something like that, which means try to infer this by the next things that I'm providing. So for getting this thing, it should also be something that says that I returns an inverse for this operation. And now it's an exercise of whether we need to mention unit here or not. Sorry, not unit E with my things. Yes?
If we want to be like write what we need and then see if it's necessary, we should mention
the identity.
Yeah.
I mean, okay, this is a good exercise. Like when you think of semi-groups, it's a binary operation that's associative. And then you think of monoids, you add identities to semi-groups, let's say, and you get monoids. And then you add the inverses and you get groups. But somebody could ask, could I do it the other way around? Could I first add inverses and then add an identity? And like a first reaction should be Manol's reaction, like how will you add first inverses? Because even if I want to say the word that something is an inverse of the other thing, I need an identity. I mean, that's the objection. It's not the case. And it's not so difficult. It's a fun exercise to try to define what it means for this operation to be invertible on the left or on the right, whatever, without having access to an identity. I mean, if you think about it for like 10 minutes, I think you'll figure it out. But, so technically, I do not need this, but if you want to put it for traditional reasoning, let's say the tradition reasons, we can put it like that. So essentially,
Wouldn't this be the same argument as for do we need to mention the identifier isomorphisms or not? Isn't it the same argument?
what? Sorry?
When we were talking about isomorphisms, we were saying that, we can get some things for free by isomorphisms respecting the identity.
Okay.
Or homomorphisms maybe, but the operation, by the respecting the operation, we get things for free. But we should mention them in the definition.
Oh, okay. No, it's different. I mean, you could have like a structure that doesn't have an identity, and still the operation has, and still there is an inverse operation. I mean, we need to. I probably will give a spoiler if we.
Here, I mean, specifically here, we want to say that this is a group, which means that this thing is an inverse operation with respect, an inverse function with respect to this operation and this identity.
Yes, yes.
Is that like you want to say it? Even if it's unnecessary to be specific, like if that's specific. It makes sense.
It does make sense. Maybe. I don't have a good answer for that. I mean, you say it's closer to the heart of what a group is, I suppose. Yeah, you're right. However, let's say if for some reason I first define groups, and I want to see what happens if I forget some parts, I can get monoids, and I can get semi-groups, but I will not be able to get the other thing because I embedded in my definition of inverses the necessity for an identity, which is like kind of artificial, but it's fine. I mean, probably in most ways that you will see a definition of a group, you will see it like that, and the equation that this will be like inverse, the inverse of, x. If you operate this with x, this should be the identity, and the other way around. It's a left inverse and a right inverse. So this is, most of the times you see it like that, and if you want to translate that, you will translate it like that with all of these things. Lazarus, you were trying to say?
Well, I can think of some examples where you can define inverses without...
This is you will reach an example. I mean, if you try to define it.
I have one in mind, but
okay.
My question is, can you always do that? Define the inverse without...
I mean, you can define what it means for a binary operation to be for a unary operation to provide inverses for a binary operation without necessarily having access to an identity. Maybe you don't know which one it is, or without even existing an identity element there. In this sense, does that make sense?
Is this always possible?
I mean, you can define what it means. Maybe this thing doesn't exist, but I mean, you can define the meaning of the expression. Like, yeah.
What I'm trying to ask is that is there
Maybe
a better way to define what an inverse is than this?
I have already regretted mentioning this thing. I should have stayed there. Let's try to forget it. Maybe I also messed something up here in what I claimed. Let's leave it as fun exercise. Try to express the idea of being an inverse without mentioning identity. And we can come back to that or get it to Zulip. It's like, I'm already like 5 times, I have stolen like 5 times from your life or something like that. Does it make sense, the type-theoretic way of saying that something is a group, and I will give good names to these things like associativity or whatever, and so this means that if I have a group, and I write something like that, you know I'm referring to a proof of this associativity of the group. Because in order to give me a group, you gave me 9 things. How many things were there? Like 4 plus 5, 6, 7, 8, 9. Okay, these are essentially pairs. That's why I say 6, 7, 8, 9. So you're given me 9 things essentially, and I have immediate access to all of them with good names and all those things. When I want to prove something, and I have a group G and a group H, I have all those things. And when I have like a homomorphism between a group G and a group H, phi, this also has some extra data, so this will end up being something like there's an underlying function, a carrier function, which is just something of this type. And all the things that it needs to respect, like respect op and respect unit and respect inverses. Maybe I have just a respect thing that it's a triple, so I want to access the respect of the op blah blah. So phi, the actual homomorphism, also is a tuple, has a function, and a proof, a construction that it respects the operation of G in H, and respects everything that needs to respect. Okay, so we discussed this, if you like, in Zulip, or maybe on the next. There was a question about something that was in the exam, like how to prove that from exponentials you get distributivity. I want to see this, so I will mention it eventually in one of the class, probably the next one. But yeah, so we end this class here, and see you Tuesday, and I hope that we'll start playing with some proof assistant on Tuesday and Friday as well.